In the silent darkness beyond our atmosphere, past the faint blue glow of Earth, lies an ocean with no horizon. It has no surface, no shoreline, and no end that we can see. For as long as humans have looked up, we've asked the same impossible question. How far can we go? For most of history, the answer was simple. Not far at all. We were bound to our planet, prisoners of gravity and atmosphere, dreaming of distant stars we could never reach. But dreams have a way of reshaping reality. In the 20th century, we lit fire beneath steel and touched the sky. Rockets carried us into orbit, and for a brief moment in 1969, human footsteps pressed into alien soil the dusty gray regolith of the moon. That single step transformed the human story. Suddenly, the cosmos was not unreachable. It was a destination. Yet, decades later, we remain tethered. The moon was our first leap, but our boots have not pressed into the red sands of Mars, nor have our eyes gazed firsthand upon the icy cliffs of Europa or the methane seas of Titan. Even robotic explorers, Voyager, Pioneer, New Horizons, despite their decades of silent travel through interstellar darkness, are still only brushing the edge of the solar system. If machines take half a century to reach the boundary, how far could fragile humans really travel? And what lies beyond the pale limits of our reach? Imagine holding a map of the universe. Our solar system is a speck, orbiting a single yellow star among hundreds of billions in the Milky Way. The nearest star system, Alpha Centauri, lies just 4.37 light years away. A small number, 4, a digit we can hold in the palm of our hand. Yet, in practical terms, it is a gulf so immense that crossing it with current technology would take tens of thousands of years. The nearest star might as well be infinity. And Alpha Centauri is not even far. It's a neighbor's porch light barely visible down the street. The true scale of the galaxy stretches 100 light-years across. The nearest large galaxy, Andromeda, is 2.5 million light-years away. And beyond that, billions more. The universe tempts us with impossible distances. Every telescope image of deep space shows countless galaxies, each one a city of stars, each star hosting its own worlds. If our minds crave exploration, then the cosmos is a cruel teacher, dangling treasures beyond reach, but perhaps not unreachable forever. The question is not whether we can travel far in space. The question is, by what limits will we be bound? By biology? By physics? Or by imagination? The first barrier is time. Rockets, the very machines that carried us to the moon, are powerful, but pitifully slow against cosmic scales. A spacecraft launched today using chemical propulsion would take more than 70 years to reach Alpha Centauri. For perspective, 70 years ago, humans had not yet painted caves or built villages. Our species itself has changed since then. Would any journey spanning such epochs even count as travel? Or would it be the drifting of seas in the cosmic wind? Scientists imagine alternatives: nuclear propulsion, antimatter drives, solar sails pushed by lasers, even theoretical warp engines that bend space-time itself. Each promises shortcuts through the abyss, but each carries its own paradoxes. Nuclear rockets demand fuel so dense it could level continents. Antimatter, the most efficient fuel possible, annihilates on contact with ordinary matter, requiring containment fields stronger than any material we can currently produce. Solar cells need lasers the size of cities to push a wafer-thin craft across the void, accelerating to fractions of light speed, but only for machines, not fragile humans. Even warp drives, once confined to science fiction, exist in the margins of physics papers. Equations suggest they might be possible if we could harness forms of energy that warp space-time, compressing space ahead of us, expanding it behind, creating a bubble that carries a ship faster than light without technically breaking Einstein's speed limit. But these equations demand negative energy, exotic matter, that we have never observed in quantities sufficient for even a grain of sand, let alone a starship. Still, the possibility lingers. And that possibility forces us to ask not only how we might travel far into space, but why. Will we seek new homes as Earth warms and resources dwindle? Would we pursue knowledge for its own sake? to stand on alien shores and look back at the Milky Way rising? Or would we be compelled outward by something deeper, something written into our DNA? The same instinct that drew our ancestors across oceans and deserts when they had no maps and no guarantees of survival? History suggests that when humans can go, they eventually will. The Polynesians sailed across the Pacific with only stars and currents to guide them. The first hunter-gatherers crossed land bridges into new continents, not knowing what lay ahead. Each time, the horizon was an invitation, not a wall. Space is the ultimate horizon. And yet, unlike oceans or continents, it confronts us with laws of physics that feel absolute. But what if they aren't? What if our understanding of distance and time is limited by the boundaries of our current science? Just as ancient sailors believed the ocean ended in waterfalls, we might be trapped by illusions of impossibility that future generations will shatter. After all, only a century ago, flight across Atlantic seemed as daunting as interstellar travel seems now. Consider this. If we could accelerate to just 10% of the speed of light, Alpha Centauri would be reachable in about 40 years. Still a lifetime, but no longer an eternity. At 50% the speed of light, the journey shrinks to under a decade. At the speed of light itself, 4 years, and if warp technology ever became real, if space-time itself could be reshaped, the journey might take days or even hours. But speed is not the only barrier. Human bodies are frail, designed for Earth's gravity, shielded by its magnetic field, evolved to breathe its air. Beyond our atmosphere, radiation pierces flesh, bones weaken, muscles waste. Time stretches into decades. Food, water, air, all must be carried or produced. A starship is not merely a vessel. It is a world entire, an arc carrying generations through endless night. So, how far can we really travel in space? The truest answer may not depend on rockets or physics at all. It may depend on us, on whether we can imagine lives measured not in years but in centuries, not in destinations but in journeys. Whether we can accept that travel to the stars might mean never arriving ourselves, but planting the seeds for descendants we will never meet. The journey outward is as much about philosophy as it is about engineering. Because distance in space is not just measured in kilometers or light years. It is measured in patience, in courage, in the ability to look at an impossible gulf and step forward anyway. And so we return to the question, not how far can we travel, but how far are we willing to go? The first step to truly leaving our cradle may not involve speed at all, but time. If we cannot cross the gulfs between stars within a single lifetime, then perhaps we must stretch our lives, or surrender to the idea that no single human will see both departure and arrival. This is the philosophy of the generation ship, a vessel so vast it becomes a floating civilization, carrying thousands of people who live, work, and die while their descendants continue the voyage. Imagine a ship kilometers long, with rotating habitats to simulate gravity, forests to recycle air, oceans in miniature to stabilize climate. Inside, it will feel less like a spacecraft and more like a world unto itself. To those born within, the stars outside might be myth, destinations spoken of like sacred prophecies. For them, the journey is not a means to an end, but the entirety of existence. Such ships could drift for centuries, even millennia, their populations, evolving cultures, languages, and traditions entirely separate from the Earth that launched them. But even a generation ship cannot escape the tyranny of physics. The resources required to build one would dwarf the output of entire nations. Its engines must burn for decades just to accelerate to a fraction of light speed, and then decelerate again at the journey's end. And what if a single failure, a reactor breach, a plague, a mutiny, ended the mission halfway? Then the stars would inherit a lifeless ark, frozen evidence of human ambition scattered in interstellar darkness. The romance of the concept collides with the cold reality of scale and risk. Some imagine a different solution: sleep. If we cannot extend lifespans or endure centuries awake, perhaps we can slip into oblivion and wake when the stars have changed position. Science fiction has made cryogenic sleep familiar chambers, where travelers slumber in frost until a computer whispers them awake. In reality, cryonics remains crude. Freezing living tissue shreds cells with ice crystals. Reviving a human being from suspended animation is far beyond our capabilities. And yet, nature provides examples that hint it might be possible. Frogs that survive frozen winters. Microbes revived after thousands of years locked in Antarctic ice. Tiny creatures called tardigrades that endure the vacuum of space. Desiccated and dormant, springing back to life with only a drop of water. If biology already holds these tricks, could human science unlock them for us? Could the long sleep one day be real? Even if we could sleep through centuries, time itself would conspire to distort the journey. Einstein's great revelation relativity tells us that as we approach the speed of light, time dilates. To those on board, the clock ticks slower. A starship traveling at 90% of light speed could reach Alpha Centauri in less than 5 years from the crew's perspective, though back on Earth, more than 4 years would still pass. Push closer to the cosmic limit, 99.9% of light speed, and the effect grows astonishing. Whole decades might vanish for Earth while only a handful of years pass inside the ship. From the crew's perspective, the galaxy itself contracts. Journeys of thousands of light years become manageable within a single lifetime, though only for them. The cost is severing themselves from the world behind. The Earth they departed would age into an unrecognizable future. Its civilizations risen and fallen, its languages transformed, its people perhaps extinct. The travelers would arrive at their destination, but they would arrive alone, carrying a past no one remembers. This paradox reveals the cruel poetry of space. It grants us a dream of travel, but punishes us with isolation. To go far is to abandon what we know. To stay close is to surrender exploration. Either way, the journey demands sacrifice. And yet, the allure persists, because the stars themselves whisper possibilities. When Voyager 1 turned back in 1990 and captured the pale blue dot, Carl Sagan reminded us that Earth is a mote suspended in a sunbeam. To remain forever bound to that mote is to deny the immensity of everything else. Our curiosity is not satisfied by orbiting our own star. It demands more. So perhaps the real question is not whether physics allows us to travel far, but whether culture does. Would we, as a species, commit to missions spanning centuries? Would we pour resources into a starship when we still struggle to feed our own populations? Would we accept that those who depart will never return, and that those who arrive will never know the world that launched them? For the first time in human history, these are not abstract questions. They loom on the horizon of the coming centuries, as real as the rockets we already launch. Every path forward reveals both promise and peril. Generation ships risk decay across time. Cryosleep risks technological failure. Relativistic travel severs ties with our home. Yet each option cracks open the door to the stars. Each transforms the impossible gulf into something less than infinity. And if history shows anything, it is that humans have always stepped through doors once they were ajar, even when danger waited on the other side. We stand now in a liminal moment, perched between planetary adolescence and cosmic adulthood. Our machines have already ventured farther than we have. Our names and messages, etched onto metal plates aboard Voyager and Pioneer, drift outward through interstellar night. We have, in a sense, already begun our journey, but only through proxies, fragile messengers of silicon and steel. The question that remains is whether we will follow them, flesh and blood riding fire into the abyss. If we do, it will not be for comfort, it will be for meaning. Because the measure of how far we can travel is not found in engines or equations, but in our willingness to let go of certainty and embrace the unknown. If generation ships and cryosleep represent ways to endure the slowness of our current rockets, then the next frontier of thought lies in propulsion itself. What engines could push us beyond the crawling pace of chemical fire, beyond the patience of centuries? The most obvious step forward is nuclear fusion. On Earth, we struggle to harness the same process that powers the stars, confining plasma hotter than the sun inside magnetic cages. We dream of reactors that could provide near limitless clean energy. If such power could be controlled, it might also drive a ship. Imagine a vessel with a fusion engine, spewing out exhaust at tens of thousands of kilometers per second. A starship using fusion could cut a journey to Alpha Centauri down from millennia to mere decades. Suddenly, the gulf shrinks to a span that a single crew could endure. But fusion is a promise we have chased for decades without catching. Our laboratories achieve reactions for seconds at a time, not the continuous, controlled burn a starship would demand. A practical fusion rocket would require engineering far beyond anything we possess today. The irony is painful. The power to cross the stars already shines above us, written in every sunrise. Yet we cannot hold it in our hands. Beyond fusion lies antimatter. In physics, antimatter is not fantasy. We create it routinely in particle accelerators. For every particle of matter, there exists its opposite twin, identical in mass but opposite in charge. When matter and antimatter meet, they annihilate in a perfect conversion of mass to energy, Einstein's equation, in its purest form. No fuel could be more efficient. A gram of antimatter colliding with a gram of matter will release energy equivalent to a nuclear bomb. Scale that to kilograms, and you could drive a ship to a significant fraction of light speed. The stars themselves would no longer be impossibly distant. And yet, the dream collapses under practical weight. To produce a single gram of antimatter would require the world's most powerful accelerators running for years, consuming energy on a planetary scale. Storing it would be even harder. No container of ordinary matter can touch any matter without instant annihilation. It must be suspended in magnetic fields with absolute precision. A failure would not mean a broken engine, it would mean an explosion that vaporizes the ship in an instant. Antimatter remains the wildest of fuels, perfect in theory, catastrophic in reality. Some propose a gentler vision. Solar sails. These are not engines at all, but vast sheets of reflective material stretched across kilometers, pushed by sunlight itself. Photons, though massless, carry momentum. Strike a mirror with enough of them, and the mirror will drift forward. On Earth, the push is imperceptible, but in the vacuum of space, with no resistance, the pressure accumulates. A sail could accelerate for years, reaching extraordinary speeds without a drop of fuel. The concept has already been tested. Japan's Ikaros mission unfurled a sail in 2010 and successfully steered it with sunlight. Future visions imagine sails pushed not just by the sun, but by colossal lasers stationed in Earth orbit, beaming power outward to propel wafer-thin probes at a fifth the speed of light. Such probes could cross to Alpha Centauri in just 20 years. For machines, the dream is within reach. For humans, the sail may never be strong enough. The mass of a cruise ship would demand a laser the size of a continent, focused across light years with impossible accuracy. Once again, the abyss yields to machines more easily than to flesh. At the edges of imagination lie concepts that strain even physics itself. Warp drives, wormholes, the bending and stitching of space-time. These are the tools of science fiction, yet hidden in equations. Fragments of possibility glimmer. A warp drive, in theory, creates a bubble around the ship, contracting space in front while expanding it behind. The ship itself does not move faster than light, but the bubble does. The universe carries it forward, like a surfer riding a cosmic wave. To those on board, the stars would blur past. To distant observers, the ship would seem to break Einstein's barrier. The mathematics works, but the requirements are absurd. Energy equivalent to the mass of entire stars, and exotic forms of matter with negative energy density that no laboratory has ever glimpsed. A warp drive exists not in our factories, but in the ink of our notebooks. Still, the very fact that physics does not forbid it outright keeps the dream alive. Wormholes offer another path. If space is a fabric curved and bent by mass, then perhaps it can be folded. Two distant points could be connected by a tunnel, a throat through space-time. Enter one end, and you emerge instantly at the other, regardless of the distance between. Such shortcuts appear in Einstein's equations as well, though with the same problem. They require exotic matter to keep their throats open. Without it, they collapse the moment they form. If such tunnels exist naturally, they may be microscopic, flashing into and out of existence on quantum scales. Could an advanced civilization learn to stabilize them, to stretch them large enough for ships? If so, distance becomes irrelevant. The galaxy itself becomes a connected web. The dream is intoxicating, but again, it hovers just beyond our reach. Every step outward into speculation reveals a pattern. Chemical rockets gave us the moon. Nuclear propulsion may give us the stars. Antimatter and exotic physics hint at a galaxy. Each rung of the ladder requires leaps in understanding and power that dwarf the last. And yet history teaches us that barriers once considered absolute often fall. Flight, space, nuclear fire. Each was impossible until it wasn't. The question is not whether warp drives exist today. It is whether, in 1,000 years, children will look back at our doubts the way we look back at sailors who feared the edge of the world. Still, these dreams carry their shadows. Speed brings dangers as well as hope. A ship moving at a tenth the speed of light strikes interstellar dust with the force of a bomb. Even a grain of sand could punch through hulls like bullets through paper. Radiation from the cosmic background increases with speed, battering flesh and electronics alike. To race the stars, we must not only build engines, but shields, armor, and perhaps entire artificial magnetic fields to guard our fragile bodies. To travel far is not only to conquer distance, but to endure the hostility of the void. How far can we really travel in space? The answer stretches between cold equations and burning dreams, between the engines we can build and the physics we cannot yet touch. Each concept, fusion, antimatter, sails, warp, offers a vision of what might be. Each stands as a reminder that the universe is both inviting and forbidding. To reach the stars, we must not only solve engineering puzzles, we must confront the limits of imagination itself. Because the stars are waiting, whether we arrive crawling, sailing, or warping, the cosmos cares little. The only true question is whether we dare to try. The engines of imagination may promise us paths through the stars, but even if tomorrow we could light a fusion rocket or open a wormhole, one truth remains: we cannot escape ourselves. Our bodies and minds, sculpted by millions of years under Earth's sky, are fragile things. Space exposes that fragility with brutal clarity. Beyond the thin shell of our atmosphere, radiation floods unprotected flesh. Cosmic rays, invisible and relentless, slice through DNA like knives. Astronauts who spend months aboard the International Space Station return with higher cancer risks, degraded vision, and damaged cells. In interstellar space, shielded only by metal walls, the assault would be unending. A journey of decades could transform a crew into something less than human before they ever arrive. The solutions are costly. To block radiation, a ship might need meters of water surrounding it, or magnetic fields as strong as Earth's own, bending deadly particles away, but weight is the enemy of travel. Every ton of shielding demands more fuel, more energy, more compromise. The paradox is cruel. The faster we wish to go, the less we can carry. And yet the faster we go, the more protection we need. To endure the abyss, we may need to carry pieces of Earth, itself oceans for shielding, soil for growing food, air thick enough to breathe. A starship becomes less like a vehicle and more like a fragment of our planet torn free, sailing on a cosmic tide. Even if we solve radiation, gravity remains. In orbit, astronauts float in weightlessness. To the eye, it looks like freedom, but inside their bodies, disaster unfolds. Muscles waste away, bones dissolve, the heart itself weakens, pumping less efficiently. After a year, the body is aged by decades. On a multi-decade voyage, without intervention, travelers might arrive unable to walk, their skeletons hollow, their biology broken. Artificial gravity is no simple matter. A rotating habitat can mimic Earth's pull through centrifugal force. But the structure must be enormous, spinning steadily for years without failure. A single malfunction could leave travelers tumbling weightless, their bodies deteriorating as the stars crawl by. Gravity is not just a comfort. It is a requirement written into every cell. Food and air form the next chain. On Earth, we breathe without thought, eat without worry. In space, every breath must be earned. A closed ecosystem is brutally unforgiving. Plants recycle carbon dioxide into oxygen. Waste is broken down into nutrients. Water cycles endlessly. The balance is precise, a knife edge between life and death. One disease among crops, one failure in circulation, and the system collapses. On a ship meant to endure centuries, that collapse would mean extinction. The smallest ecosystem humanity has ever built, the biosphere. Two experiments in Arizona struggled for 2 years before oxygen levels fell and crops withered. To carry Earth into the stars is not merely technical, it is biological alchemy. And yet, even if bodies survive, minds may falter. Isolation is poison. Months aboard the ISS tests the strongest spirits. Despite constant contact with Earth, imagine years without blue skies, without forests, without rain. Imagine a child born aboard a generation ship, growing beneath metal ceilings. Their only view of the universe, the cold light of stars beyond the window. What culture will they create? What faith will they feel human? Or something else entirely, shaped by an environment that no ancestor ever knew? For them, Earth will be myth. Home will be a machine. Psychologists warn that confinement breeds conflict. In polar stations and submarines, small crews stray under stress even with escape possible. On the starship, there is no escape, no retreat. Every argument echoes through generations. A feud might outlive its founders, shaping the politics of a world in miniature for centuries. The ship is not only a machine, it is a society. Its survival depends not just on engineering, but on governance, cooperation, trust. To fail in these is to doom the journey more surely than engine failure. This raises a profound truth. To travel far in space, we may need to change ourselves as much as we change our ships. Genetic engineering could strengthen bones, resist radiation, slow aging. Drugs might enhance cognition, suppress aggression, expand lifespans. Some dream of merging with machines, replacing fragile biology with silicon and steel. Consciousness carried not in neurons, but in circuits. If the flesh cannot endure centuries, perhaps information can. A crew might leave Earth human and arrive transhuman, their descendants unrecognizable to the world that launched them. But transformation carries its own risks. If the humans who depart are not the humans who arrive, then who has truly traveled? Is the journey a continuity of identity, or a relay where one version of humanity passes a torch to another until the final runner steps onto an alien shore? Perhaps this is the secret cost of interstellar travel. Not merely distance and time, but the surrender of ourselves as we are. To reach other stars, we must let go of the idea that we will remain unchanged. The challenges of body and mind do not forbid the journey. They illuminate it. They reveal that the greatest barrier to the stars may not be physics, but humanity itself. Engines can be built. Fuel can be found. Equations can be solved. But will we endure the silence, the confinement, the separation from Earth across centuries? Will we remain whole or fracture into something new, something unrecognizable? The stars do not ask these questions. They burn indifferent, scatter across the black. The questions are ours alone, and the answers will determine how far we can really travel. Because distance is measured not only in light years, but in the resilience of bodies, the strength of minds, and the willingness to accept transformation. The farther we go, the less human we may remain. And perhaps that is the price. When we speak of traveling to the stars, we imagine ourselves aboard the ships, looking out through windows as alien suns rise. Yet even now, our farthest emissaries are not human. They are machines. Voyager 1, launched in 1977, has traveled more than 14 billion miles from Earth. It drifts in interstellar space, carrying with it a golden record of sounds and images from our world, a bottle cast into an infinite ocean. Voyager will outlast us all. Long after Earth has changed beyond recognition, the probe will continue, silent and tireless, orbiting the center of the galaxy for billions of years. In a sense, humanity has already begun its interstellar journey not with flesh, but with circuits and metal. Machines care nothing for radiation. They do not need air or water or food. They do not sicken in weightlessness or crack under loneliness. They endure cold, heat, vacuum. Their patience is eternal. Where a human crew will face torment across centuries, a probe feels nothing. This is why some scientists argue that the true path to the stars is not through us, but through the machines we create. They can be built smaller, lighter, faster. They can accelerate to fractions of light speed without worrying about g-forces tearing apart fragile tissue. They can be frozen and reawakened by a flicker of power. And unlike us, they do not die. Already we imagine a future where fleets of robotic probes spread like spores across the galaxy. Miniaturized craft, each no larger than a microchip, driven by solar sails and laser beams, could be sent by the thousands toward nearby stars. Most would fail, burned by cosmic rays or lost to the void. But some would survive, arriving decades later, transmitting back images of alien worlds. They would be humanity's eyes, looking outward on our behalf, and they would not stop. Once they arrived, they could build more of themselves, harvesting resources from asteroids, duplicating endlessly. In time, they could saturate the galaxy, exploring every system, cataloging every world. Humanity might never leave Earth in person, and yet our machines could become ubiquitous, our presence written across the stars in silicon rather than blood. But this vision raises unsettling questions. If machines explore, what place remains for us? Will we become like parents left behind, watching children leave without us? Some argue that machines are not replacements, but extensions, that their discoveries are ours, that their vision is our vision. Yet the boundary blurs when machines gain autonomy. Artificial intelligence grows more sophisticated every year. One day, probes may not only travel for us, but think for themselves. They may decide what to study, what to transmit, what to build. At what point does their journey cease to be ours? At what point does humanity's legacy become theirs and not our own? Perhaps the solution lies in merging. Already, humans use machines to extend memory, to amplify senses, to calculate what we cannot. In the future, the line may fade entirely. Minds could be uploaded, consciousness transferred into digital form, writing the circuitry of machines instead of fragile neurons. If that is possible, then we would not send robots instead of us. We would become the robots. Our thoughts could cross the stars without bodies, encoded in patterns of light, transmitted at nearly the speed of radio waves. A human mind could reach Alpha Centauri in 4 years, not 40,000, carried as information, awaiting reconstitution on the other side. The traveler would not step off a ship. They would awaken from transmission, their mind restored in an artificial vessel. Identity would become fluid, unmoored from biology. Distance would lose its tyranny, and yet this possibility unsettles as much as it excites. If the mind can be copied, transmitted, multiplied, then what does it mean to be you? If one version of your consciousness awakens around another star, while another remains on Earth, who is the traveler? Who is the original? Does continuity of thought make identity? Or is identity something that cannot be replicated? In seeking to reach the stars through machines, we may unravel the very meaning of self. Even without these philosophical depths, the advantage of machines is undeniable. Voyager has lasted nearly 50 years. A human traveler could not. New Horizons took just 9 years to reach Pluto, and it will drift onward for centuries. A crew could never endure such silence. Machines may already have shown us the path. To go far, surrender the need to go in person. Let machines carry our presence instead. Perhaps that is enough. After all, if a probe carries human music, human images, human thought, does it matter that the vessel is not alive? Is not the record of our existence itself a form of travel? But for some, this answer is hollow. We are explorers not only in mind, but in flesh. To see with our own eyes, to step with our own feet, to breathe the air of another world, that is the dream. No machine, however faithful, can give us that. The tension will remain between the efficiency of machines and the yearning of humans, between the cold endurance of silicon and the warm fragility of flesh. Which path we choose may decide not only how far we travel, but what kind of species we become. The machines have already left. They carry our signatures into interstellar night. The question now is whether we will follow them or whether the true heirs of the stars are not us at all, but the minds we create. If so, our journey might already be over. And yet, if even one human someday stands beneath an alien sun, then the machines will have been only scouts preparing the way. Both futures remain possible, written in the silence between the stars, waiting for us to decide. The scale of space is the quiet adversary behind every dream of travel. We can imagine ships, engines, and even transformed humans or machines, but the universe itself remains what it is, vast beyond comprehension. Our nearest star, Alpha Centauri, seems unimaginably close compared to the gulfs that follow, yet even it is 4 light years away, 40 trillion kilometers. That distance is so immense that every metaphor collapses. If the sun were the size of a coin, Alpha Centauri would be another coin 400 kilometers away. And that is just the first step. Beyond it, stars scatter like dust for tens of thousands of light years in all directions, stitched together into the luminous spiral of the Milky Way. From afar, a galaxy looks compact, a glowing disk. But within it, every star is separated from its neighbor by gulfs so immense that to travel between them is to cross deserts more empty than any on Earth. 1,000 light years might sound manageable, but at the speed of our fastest spacecraft, it will still take millions of years, and 1,000 light years is only a thread of the galaxy's diameter. The Milky Way itself stretches over 100,000 light years, a rotating storm of hundreds of billions of stars. Even if we master light-speed travel, it would take a human lifetime to cross from one side to the other. The scale renders even the boldest visions fragile, and yet the galaxy is only a neighborhood. Beyond lies Andromeda, the great spiral 2.5 million light years away. Its stars, more than 1 trillion of them, burn in silence, and one day, its entire galaxy will merge with ours in a slow cosmic dance. But to reach it by ship is to embrace impossibility. 1 million light years is a distance no human can meaningfully grasp. It is not measured in journeys, but in epochs. Civilizations could rise and fall 1,000 times over while a single vessel drifted the gulf. To speak of traveling there is to imagine becoming something beyond human. Farther still, galaxies multiply endlessly. The Hubble Deep Field, a photograph that peers into a single tiny patch of sky, reveals thousands of galaxies crammed into an area no larger than a grain of sand held at arm's length. Each galaxy a city of stars, each star a potential host for worlds. Scale explodes into incomprehensibility. Astronomers estimate that the observable universe contains over 2 trillion galaxies, and beyond the observable lies even more, hidden by the limits of light and time. In such immensity, the question of how far we can travel feels almost absurd. Against a backdrop of trillions of galaxies, our ambitions shrink to sparks, but there is another boundary, colder than distance. The universe itself is expanding. Galaxies race away from us, not because they move through space, but because space itself stretches. The farther a galaxy is, the faster it recedes. Beyond a certain horizon, light from those galaxies can never reach us. They recede faster than light itself. To us, they are gone forever, not merely far, but unreachable by definition. No ship, no engine, no dream can cross that horizon. It is a wall, not of matter, but of time itself. We live inside a shrinking bubble of visibility. As the universe ages, more galaxies slip away beyond reach. Someday, only the Milky Way and its local group will remain visible. The rest will vanish into darkness, carrying their stars and worlds beyond any traveler's grasp. This realization changes the question: how far can we really travel in space? Perhaps the truest answer is not as far as imagination allows, but as far as physics permits before the universe itself pulls the rest away. Our cosmic horizon, today, is about 46 billion light years in every direction, the edge of what we can see. But we cannot go there. We can only look. Even if we build ships that reach the speed of light, we could never catch galaxies already lost beyond the cosmic expansion. The universe is not only vast, it is fleeting. The longer we wait, the more it escapes us. And yet, within this horizon lies more than we could ever exhaust. Hundreds of billions of stars in our galaxy alone, each with planets, moons, asteroids, oceans of potential. Entire histories of exploration could unfold without ever leaving the Milky Way. Perhaps it is folly to dream of Andromeda when we have not yet touched Mars. Perhaps the truth is not that we cannot go far, but that far itself is different from what we imagine. Far is not millions of light years. Far is the next system, the next planet, the next moon. In a universe this immense, even small steps are infinite. But here lies a paradox. The human mind rebels against infinity. To gaze upon billions of galaxies is to feel both awe and despair. Awe because the universe offers endless mystery. Despair because the horizon mocks us. It tells us that no matter how far we go, it will never be enough. We will never see it all. There will always be more beyond reach. The universe is both invitation and rejection, whispering, "Come find me," while retreating faster than we can chase. Perhaps, then, the measure of travel is not distance but meaning. To stand on a moon of Jupiter, to swim in the methane seas of Titan, to watch the sunrise on a planet orbiting a red dwarf, these are journeys enough. Each would change us as much as crossing galaxies. Each will remind us that the universe is not only vast but intimate. That wonder does not require infinity. It requires only that we go, and yet the dream of the unreachable lingers. We imagine alien civilizations far across the void, waiting beyond the horizon. We imagine that one day, perhaps, physics itself will reveal loopholes, cracks in the wall of expansion, wormholes, warp drives, quantum tricks we cannot yet name. Perhaps unreachable is only a word we use until the day we prove it false. Until then, the scale of the universe humbles us, reminding us that even our boldest ambitions are small against the backdrop of eternity. And still, against that backdrop, we dare to ask, how far? When we ask how far we can travel, we are also asking where we might stop. Distance itself is meaningless without destination. No one sails an ocean for the sake of water. They sail to find land. And in the endless dark of space, land means worlds. Habitable planets, places where life might bloom, where we might stand without dying in an instant. For centuries, Earth seemed unique, a solitary oasis in a desert sky. But the last few decades have shattered that solitude. The universe is not empty. It is crowded with worlds. Astronomers, using telescopes that watch for faint dips in starlight, have discovered thousands of exoplanets orbiting distant suns. The Kepler mission alone revealed more than 4,000 candidates, with countless more awaiting confirmation. The lesson is clear. Planets are not rare. They are everywhere. Statistically, nearly every star hosts them. Many stars host several. In our galaxy of hundreds of billions of stars, there may be trillions of planets. The question is no longer whether worlds exist. It is how many resemble ours. Among them, a fraction sit in the so-called habitable zone, the band around a star where temperatures could allow liquid water to pool on the surface. Earth occupies such a zone around the sun. Mars does as well, though tenuously. In theory, billions of Earth-sized planets may orbit in habitable zones across the galaxy. But habitability is not a simple equation. A planet may lie at the right distance and still be sterile. Atmosphere matters. Magnetic fields matter. The presence of water, tectonics, chemistry all shape whether life can emerge. The habitable zone is an invitation, not a guarantee. Still, the possibility alone transforms the sky. Each star becomes a question. What if? Some candidates already tantalize. Proxima Centauri b, orbiting the closest star to our own, lies in its habitable zone. Just 4 light-years away, it is the nearest potentially Earth-like world. Yet, its sun is a red dwarf, unstable and violent, blasting radiation that may strip atmospheres bare. Still, if it holds on, it might harbor oceans beneath protective skies. Other worlds orbit in the TRAPPIST-1 system. 7 Earth-sized planets circling a dim star 39 light-years away. At least 3 lie in the habitable zone. perhaps bearing water, perhaps even clouds. To travel there would be to gamble oasis or wasteland, but the gamble itself is irresistible. Beyond these, discoveries grow stranger. Planets larger than Earth but smaller than Neptune, so-called super-Earths, may be common. Some might have thick atmospheres, others vast oceans without land. Some might be locked in eternal day on one side and eternal night on the other. Others may orbit double stars, with sunsets more beautiful than any on Earth. Each world is an experiment, nature's endless variations on the theme of habitability. We know almost nothing about them, but they wait, promising wonders and dangers beyond imagining. For humanity, these worlds represent more than curiosity. They are lifeboats. Our planet is finite. Resources dwindle, climates shift, catastrophes threaten. We may endure for millennia, but not forever. The sun itself, stable now, will one day swell and consume Earth. To remain here is to accept extinction. To leave, to travel far, is to embrace survival. But survival requires destinations. A barren rock cannot sustain us. We must find worlds where seas can grow, where water can flow, where skies can shelter. The search for habitable planets is not only science, it is necessity. Yet, the irony is sharp. The very stars most likely to host habitable planets are often those least suited for us. Red dwarfs, the most common stars in the galaxy, burn dim and long. They promise stability for trillions of years lifespans far beyond our suns. But they flare violently, sterilizing worlds. Giant stars, bright and alluring, live only briefly, their habitable zones fleeting before the star swells and dies. The perfect star may be rare, stable, long-lived, quiet, and even if found, the planets themselves may not welcome us. They may hold alien biospheres incompatible with ours, microbes lethal to human cells, atmospheres toxic to lungs. To settle such worlds might mean reshaping them, terraforming, engineering climates, importing life, or it might mean reshaping ourselves. Here lies the deeper truth. To travel far is not merely to find other Earth. It is to redefine what we mean by home. Earth is unique not only for its air and water, but for how precisely it fits our biology. No other world will be the same. If we insist on Earth-like perfection, we may be disappointed. But if we learn to adapt through technology, through biology, through transformation, then many worlds open to us. Oceans of Europa beneath ice, the methane seas of Titan, the deserts of Mars. Each hostile, each beautiful, each a canvas for survival. Perhaps the question is not which planets can host us, but how we can learn to live within them. Still, the allure of a twin Earth is powerful. To step onto a world where the sky is blue, the soil fertile, the rivers flowing, that is the dream. And if such a place exists within reach, it will draw us like gravity. We do not know yet whether the galaxy holds such a paradise, but every telescope aimed skyward increases the odds. The James Webb Space Telescope peers into atmospheres of distant planets, searching for the faint fingerprints of water vapor, methane, oxygen. Future instruments will go further, detecting signs not only of habitability, but of life itself. The first discovery of alien biosignatures, even microbial, would change everything. It would mean the journey is not just outward, but toward neighbors. The search for destinations transforms the question of distance. A journey of 4 light years is unthinkable without a reason. But if Proxima b holds oceans, suddenly the distance shrinks in meaning. 40 light years is unimaginable until we imagine standing on TRAPPIST-1e watching twin sunsets. 1,000 light years is hopeless until we wonder what intelligence might await us there. How far we can really travel in space is inseparable from how badly we want what lies at the end. And so the universe tempts us. It dangles worlds like lanterns in the dark, each one a possibility, each one a story waiting to be written. We may never reach them, or we may. The stars themselves are indifferent. The choice, as always, is ours. If planets are common and habitable worlds are plentiful, then a haunting silence presses in. Where is everyone? This question, known as the Fermi Paradox, sits like a shadow over all our dreams of space. If other civilizations exist, some should have risen before us. With billions of years of cosmic history, at least a few should have had time to travel far, to spread across the galaxy, to leave unmistakable traces. A single star-faring species could, in theory, colonize the Milky Way in a few million years a blink compared to the age of the galaxy. And yet, as we look outward, we see no great empires, no megastructures, no signals shouting across the stars. The galaxy remains quiet, too quiet. The silence forces us into speculation. Perhaps intelligent life is rare, vanishingly so. Perhaps Earth is not just one oasis among many, but the only one where life climbed all the way to technology. In that case, the question of how far we can travel is not merely practical, but existential. If we are alone, then our success or failure is the galaxy's success or failure. Every choice we make reverberates across eternity. There will be no one else to carry the torch if we fall. The journey would be ours alone. But there are darker possibilities. Some suggest that civilizations do arise, but they do not last. They burn bright for centuries, perhaps millennia, before collapsing under the weight of their own power. They exhaust resources, poison environment, or destroy themselves with weapons too terrible to control. They may travel a little, even scatter colonies, but the arc is always the same: expansion, collapse, silence. If that is true, then the silence we hear is not absence, but graveyard. The galaxy may be littered with ruins invisible from here, monuments to ambitions not so different from our own. In this vision, the true limit of how far we can travel is not distance, but survival. Others imagine the silence as deliberate. Civilizations may hide. The galaxy could be full of watchers who remain quiet, avoiding detection, knowing that to reveal oneself is to risk annihilation. This is the dark forest hypothesis. Every civilization is a hunter in the forest at night. To call out is to give away your position. To reveal yourself is to invite danger. If this is true, then our broadcasts, our probes, even our dreams of expansion may already have marked us. Perhaps the reason we hear nothing is that those who shouted were silenced. In such a forest, how far we can travel might depend on how careful we are, how well we learn to move without making noise. There are stranger possibilities still. Maybe civilizations transcend physical expansion. Instead of building ships, they build inward, creating virtual worlds, uploading consciousness, living in simulations so perfect that the stars outside no longer matter. From our perspective, such civilizations vanish not because they are gone, but because they no longer care to leave their planets. In this case, the limit of travel is not physical, but psychological. Once intelligence grows powerful enough, perhaps it loses interest in the stars. Perhaps the dream of space is only a stage, not a destiny. Or maybe we are blind. Maybe the galaxy is teeming with signs, but we lack the perception to see them. Just as an ant cannot comprehend a highway, we may not recognize the fingerprints of advanced civilizations written across space. Their technology could operate at scales or in dimensions we cannot yet imagine. Their journeys may not leave trails of metal ships, but signatures in physics itself, encoded in the structure of reality. If so, then how far can we travel may already be a question too narrow. We may not even know what travel means when technology surpasses our imagination. And yet, the silence could be honest. Perhaps no one has gone far because no one can. Maybe physics itself sets boundaries that no civilization can escape. Light speed, radiation, entropy walls built into the universe. Every intelligence may discover the same constraints, build the same dreams, and confront the same futility. They may send probes, they may colonize nearby systems, but the galaxy itself remains beyond reach. Not because no one tried, but because no one could. If that is true, then our ambitions echo theirs. Our generation's ships, our fusion rockets, our dreams of warp drives, these may be rehearsals of a play performed countless times before, each ending the same way, stranded in the shallows of a cosmic ocean too vast to cross. The silence, then, is not absence. It is destiny. But perhaps destiny is not the end of the story. Even if civilizations cannot span galaxies, they may still leave whispers, relics, ruins, artifacts adrift in the void. Searching for them is part of what we call the search for technosignatures. A strange chemical imbalance in a planet's atmosphere, a glimmer of artificial light, a radio pulse, too precise to be natural, all would speak of travelers who walked this road before us. Finding them would change how we view our own limits. If others traveled only so far and no farther, then we would know our place. If others left traces across the stars, then we would know the journey is possible. The Fermi paradox cuts both ways. If we are alone, then our potential is limitless, but our responsibility infinite. If we are not alone, then we must learn what happened to those before us. Did they succeed and transcend, or did they fail and vanish? The silence offers no answer. It waits like a mirror, reflecting back our hopes and fears. In that silence lies urgency. Perhaps we are the first, perhaps we are the last. Either way, the stars remain empty until we choose to fill them. The question of how far we can travel may remain unanswered until we try, and in trying, we may discover whether the silence is destiny or warning. Until then, the night sky remains both invitation and riddle, daring us to seek its truth. Time is the invisible dimension entwined with every dream of travel. When we ask how far we can go, we rarely pause to ask how long we will remain able to try. Civilizations do not exist outside of time. They rise, flourish, collapse. Stars burn, fade, die. Even galaxies change shape, colliding, merging, transforming. To travel across light years is to wrestle not only with distance, but with the relentless flow of eras. A starship that departs today for Proxima Centauri might arrive in a few decades. But what about a journey to the center of the galaxy, 30,000 light years away? Even if some future technology reached 10% the speed of light, the trip would last hundreds of thousands of years. Who or what would endure long enough to see its end? The human species, in its current form, has existed for only a few 100,000 years. Civilization, as we define it, spans perhaps 10,000. Agriculture is younger than the pyramids, electricity younger than Shakespeare. In less than 2 centuries, we went from steam engines to nuclear weapons, from telegraphs to space probes. The pace of change is dizzying, but it is also a warning. If the next few centuries transform us as much as the last 2 have, what confidence can we have that we will remain recognizable even 1,000 years from now? By the time a ship reached a distant star, the society that launched it might have changed beyond recognition or vanished entirely. The travelers might arrive carrying the legacy of ghosts. Some thinkers imagine this as a race. A ship leaves Earth, but by the time it reaches its destination, new technologies back home may have surpassed it. Faster ships could be launched later, overtaking the original. The pioneers become stranded relics, outpaced by their successors. This is the weight calculation. Why launch now, when tomorrow's ships may be faster? But tomorrow always promises more. If we wait too long, we may never leave at all. The dilemma is eternal. Act with what we have, or gamble on what time may offer. Civilizations themselves are fragile threads in this tapestry of time. We look at our society and imagine continuity stretching centuries forward, but history tells another story. Empires fall, cultures fracture, knowledge is lost. Rome fell, the Maya collapsed. Entire peoples vanished, their stories reduced to ruins and silence. Why assume our own civilization is immune? A ship launched today might arrive to find Earth silent, its home long destroyed by war, by climate, by neglect. To travel far in space may require not only engines, but the ability to maintain a stable civilization across geological time. That may be the hardest challenge of all. But time also offers opportunities. Stars live for billions of years. Red dwarfs, the most common stars, will burn for trillions. If humanity or its descendants can survive long enough, the galaxy itself becomes a playground lasting longer than Earth's entire history. Even if expansion is slow, crawling across a star every 1,000 years, given time enough, even a patient civilization could spread everywhere. The question then becomes, can we last? Are we capable of thinking not in centuries, but in millions of years. The scale of cosmic time dwarfs even imagination. Dinosaurs ruled Earth for 160 million years, a span 1,000 times longer than recorded human history. If intelligent life lasts as long, it could scatter seeds across the entire galaxy, even with modest technology. Perhaps this is the real lesson. Distance matters less than endurance. The stars will wait. The only question is whether we remain. Yet endurance itself may change what we are. Evolution does not stop. Our descendants may not be human in the way we define it now. They may be engineered for longevity, adapted for radiation, resistance, or integrated with machines. A species designed to think in millennia, not decades, could treat time differently. What feels impossible to us may feel natural to them. For such beings, journeys of thousands of years might be ordinary. No stranger than the sea voyage was to our ancestors. To ask how far we can travel is to ask what we will become to make that travel possible. Even the universe is subject to time's erosion. Stars burn out, galaxies drift apart. Eventually, trillions of years from now, darkness will dominate. Energy will scatter, entropy will rule. In that final era, travel itself may become meaningless. No fuel, no destinations, only fading embers. If intelligence still exists, then it will face limits not just of distance, but of existence itself. Against this backdrop, our own ambitions are fleeting sparks. To dream of traveling far is to dream against the tide of eternity. And yet, time also grants perspective. Perhaps we do not need to cross galaxies. Perhaps the act of survival itself lasting long enough to adapt, to evolve, to remain is the real journey. If we endure millions of years, the stars will come to us. The sun will change, Earth will shift, and necessity will push us outward. Distance may be infinite, but time will force our hand. The question is not whether we can travel far, but whether we can outlast the clock that ticks above us all. The future stretches like a road hidden in fog. Perhaps we will perish soon, our ambitions erased. Perhaps we will survive and scatter not only across space, but across time, leaving echoes in eras yet unborn. How far we can travel is inseparable from how long we can remain. Time is a silent partner to distance, the second half of the riddle. The stars are not only far away, they are waiting, patient, indifferent, knowing that only those who master time will ever reach them. Energy is the currency of travel. Every dream of crossing the void, whether by chemical rockets or warp drives, reduces to the same question: how much power can we control? On Earth, energy is a matter of convenience, burning coal, splitting atoms, channeling rivers. In space, energy is survival. To accelerate a starship to a significant fraction of light speed requires not just enormous power, but precision, sustainability, and mastery over forces that dwarf anything we have ever attempted. Distance may tempt us, and time may test us, but energy is the gatekeeper that decides whether the journey begins at all. Consider our most familiar tool, the chemical rocket. The Saturn V, which carried humans to the moon, burned through 20 tons of fuel per second. Its payload, once in space, was minuscule compared to the fuel that lifted it. Chemical rockets are triumphs of engineering but dead ends for interstellar travel. The energy density of chemical reactions is simply too low. To reach even the nearest star, a ship would require more propellant than exists on Earth. No amount of optimization changes the arithmetic. If chemical rockets are candles, then interstellar travel demands stars. Nuclear power is the next rung. Fission, the splitting of heavy atoms, offers millions of times more energy per reaction than chemistry. It could, in principle, power engines that burn for years, accelerating slowly but relentlessly until incredible speeds are reached. Fusion, the joining of light atoms like hydrogen, promises even greater yields. A ship driven by fusion could sip fuel from the most common element in the universe, hydrogen itself. Entire concepts like Project Daedalus were built on this dream. A probe propelled by fusion explosions, riding waves of fire toward Barnard's star. Such a craft could reach 12% of light speed, arriving in half a century. Yet, fusion remains elusive on Earth. We have yet to harness it in a stable reactor, let alone in a Starship engine. Energy is abundant in theory, but scarce in practice. Beyond fusion lies antimatter, the most potent fuel we know. When matter and antimatter meet, they annihilate completely, converting mass into pure energy. A few grams of antimatter could match the destructive force of a nuclear bomb. A ship fueled by antimatter could, in principle, accelerate to half the speed of light or more. The problem is supply. Antimatter does not exist naturally in quantity. We must create it in particle accelerators, and the amounts produced so far are measured in nanograms, at costs beyond comprehension. To fuel even a small starship would require factories capable of generating tons of antimatter, a project that would make the construction of pyramids look trivial. The universe gives us energy, but it hides it behind walls of scarcity and difficulty. Yet, energy is not only about propulsion, it is also about endurance. A starship must power life support, shields, communication, repair systems. For centuries or millennia, it must sustain an artificial world, carrying forests, oceans, and light through endless night. Solar power, so abundant near Earth, fades into uselessness between the stars. Nuclear reactors may last centuries, but not forever. Exotic energy sources harvesting particles from the interstellar medium, tapping the quantum fluctuations of vacuum, remain speculative. A civilization capable of truly traveling far must not only master propulsion, but energy independence on cosmic timescales. Here, the scale of need collides with the scale of civilization. On Earth, our annual energy consumption is roughly 600 exajoules. To send even a modest starship to Proxima Centauri at 10% of light speed might require thousands of times more. We are barely able to power cities and industries. Yet, interstellar travel would demand planetary scale effort. Physicist Freeman Dyson once imagined civilizations that build spheres around entire stars, capturing all of their light to fuel ambitions beyond planets. Such Dyson spheres or swarms are not fanciful decoration, they may be the natural requirement for star-faring species. To travel far, you must first command the full power of suns, and what of civilizations beyond ours? The silence of the galaxy may mean that few ever achieve this mastery. To climb the ladder of energy use, from harnessing fire to splitting atoms to capturing stars, is to climb against gravity itself. At each rung, the risks grow sharper. Fail, and you burn. Succeed, and the stars open. The measure of how far we can travel may be nothing more than how high we can climb before falling. But there is another angle. What if the problem is not insufficient energy, but too much? Harnessing antimatter, capturing starlight, bending space with warp drives, each of these ideas risks catastrophic instability. A drive failure could annihilate a ship. A miscalculation could sterilize a planet. Perhaps energy mastery is the great filter, the barrier most civilizations never cross. They reach for the stars, only to find themselves consumed by their own fire. Yet hope persists. Energy is abundant if we learn how to claim it. Every star is a furnace, every black hole a dynamo, every galaxy a storm of power. We are surrounded by oceans of energy, waiting for intelligence to drink. Our current limits are not cosmic. They are local. They are temporary. If we endure, we may find ways to tap the deep wells of the universe, drawing on resources that make today's power grids seem like candlelight. The journey outward is therefore inseparable from the journey inward. To ask how far we can travel is to ask how much energy we can command, how responsibly we can wield it, how daringly we can apply it. The cosmos does not lack fuel. It lacks civilizations wise enough to use it. If we can become one, then the distances between stars will shrink. If not, we will remain earthbound, gazing at unreachable light. To speak of distance, engines, energy, and survival is to speak of the mechanics of travel. But beneath the equations lies something harder to quantify: why we go at all. Humanity has always been pulled forward by horizons, compelled to climb mountains, cross oceans, pierce skies. Yet every horizon reached only reveals another beyond it. The cosmos tempts us with horizons that may never end. To ask how far we can travel is also to ask why we should, and whether meaning can survive distances so vast they dissolve the scale of human life. On Earth, journeys had destinations. Explorers set out for new lands. Traders sought routes. Pilgrims searched for sacred places. Each journey closed a loop, linking departure and arrival. But the universe offers no such loops. It stretches endlessly, stars scattered like sparks, galaxies multiplying into invisibility. No matter how far we go, there is always farther. No traveler will reach the end. The horizon retreats forever. Does that diminish the journey or magnify it? If space has no finish line, then travel becomes less about conquest and more about continuity. The point is not to arrive, but to keep moving. Perhaps meaning lies not in destinations, but in the act of seeking itself. Yet there is another truth. Distance erodes identity. A person who leaves Earth today for another star will never return. The community they knew, the world they inhabited, will be gone long before their journey ends. They will belong neither to Earth nor to their destination, but to the journey itself. Their children may feel no connection to the world of their ancestors. For them, Earth will be a legend. 1,000 years into a voyage, the idea of home may mean nothing. 1,000 years beyond, perhaps even human itself dissolves, replaced by something new. Distance is not neutral. It transforms. The farther we travel, the less we resemble what's set out. This transformation may not be tragedy. It may be the point. Every great voyage in history has reshaped its voyagers. The Polynesians who crossed the Pacific became something different from those who stayed behind. The migrants who left Africa tens of thousands of years ago created cultures, languages, and identities that diverged until they seemed worlds apart. The same pattern may unfold on cosmic scales. Each star reached may seed a new branch of civilization, distinct, alien to its siblings. Over millennia, diversity would explode. Humanity would not be one species but many, scattered across the spiral arms like pollen. To ask how far we can travel may be less about geography than genealogy. Each distance becomes a birth, but such births raise questions of unity. If distance fragments us, does anything bind us together? Would we still recognize ourselves in those who live under alien suns? Or would they seem as different to us as we would to an ape in the forests of prehistory? Perhaps that is inevitable. Perhaps the identity of human is only temporary, a phase. We may love it, mourn it, and yet it must give way. To travel far is to let go. For some, this is unbearable. Why leave at all if the self is lost? Why not remain here where continuity and identity are preserved? But for others, this dissolution is liberation. To scatter, to transform, to become countless new forms that may be the only true immortality. The cosmos offers no promise of permanence, but it offers endless space for change. Meaning, then, becomes not the preservation of who we are, but the creation of what we might become. The philosophical challenge is this: can meaning survive without limits? On Earth, stories have beginnings and ends. Life has arcs. Civilizations have lifespans. In the universe, there may be no ends, only expansion without closure. A ship traveling forever, never arriving, may feel not like purpose, but like futility. To give meaning to infinite horizons, we must redefine purpose itself. Exploration must become not a project to finish, but a condition of existence. The journey is not what we do, it is what we are. And yet, meaning may also shrink. For the crew of a generation ship, meaning might not lie in stars at all, but in daily survival, in families, in rituals, in the stories passed down through darkened corridors. The cosmic scale may fade to background. The universe may be infinite, but for them, home is the ship itself. Perhaps this is how civilizations endure across great distances, not by carrying the weight of infinite meaning, but by finding small meanings that endure even when the stars remain impossibly far. Distance also challenges ethics. If we travel far and find worlds already alive, what do we owe them? Do we have the right to reshape, to terraform, to replace? Is our survival justification for conquest? Or must we learn to share with biospheres utterly alien? The farther we go, the more often we will face this dilemma. In our hunger to travel, we may spread like fire, consuming, or we may learn humility, becoming gardeners instead of conquerors. The choice will shape not only how far we go, but what legacy we leave behind. Ultimately, philosophy threads through every practical question. Energy, survival, distance, time, all are necessary, but none sufficient. The heart of the question lies in why. Do we travel for curiosity, for survival, for expansion, for meaning itself? Each answer changes the path. To travel far may mean scattering seeds across a galaxy. To travel far may mean building simulations so rich that the stars are unnecessary. To travel far may mean surviving long enough that distance becomes irrelevant. The answers are as infinite as the stars. And still, the silence of the night sky asks the question again. How far can we really travel? Not just in kilometers or light years, but in spirit. How far can our identity stretch before it breaks? How far can meaning survive before dissolving into infinity? The answers will not be found in physics alone, but in the stories we choose to tell ourselves as we look outward. Every dream of travel eventually collides with the walls of the universe itself. We can imagine engines brighter than suns, civilizations lasting for eons, even consciousness freed from biology. But there are boundaries written into physics that no imagination can erase. These limits are not challenges to be solved. They are the laws of reality, the framework within which all things exist. To ask how far we can really travel is, in the end, to ask what those walls allow. The first wall is the speed of light. Nothing with mass can accelerate to, let alone beyond, this limit. As you approach it, energy demands rise without bound. A ship driven ever faster requires more and more power until infinity itself is needed to cross the final threshold. Einstein's equations have withstood a century of challenges. Light speed is not simply a suggestion, it is a horizon. If it holds, then the stars will remain distant, never collapsing into easy proximity. The fastest possible journey is still slow compared to the scale of galaxies. There are loopholes, proposed warp drives, wormholes, shortcuts through space-time itself. The mathematics is tantalizing. A warp bubble could, in theory, contract space ahead and expand it behind, carrying a ship faster than light without breaking relativity. A wormhole could bridge 2 points across the universe, collapsing light years into meters. But each of these ideas requires conditions we cannot produce. Exotic matter with negative energy density, stability against collapse, control over space-time itself. They are not engineering problems so much as miracles disguised as physics. If they are possible at all, they may lie far beyond any technology we will ever wield. And if they are impossible, then the wall stands unbroken. The second wall is energy. To cross even modest distances at relativistic speeds demands staggering amounts of fuel. A starship carrying people to Alpha Centauri at 1/10 light speed would require the energy output of entire nations for years. To reach another galaxy would require power on the scale of stars. Even if physics permits such journeys, the logistics of gathering, storing, and wielding that energy may render them forever out of reach. The universe is vast, not just in distance, but in the resources needed to traverse it. The third wall is time itself. Stars burn on billion-year clocks. Galaxies rotate like slow hurricanes. Civilizations rise and fall in moments compared to this cosmic rhythm. A ship could be designed to last thousands of years, but can a culture? Can memory? To spend tens of thousands of light years requires continuity that may exceed any social fabric we can imagine. Perhaps machines can endure. Perhaps minds stored in crystal or quantum fields can wait out the ages. But even they would be tested, because time erodes not only memory, but energy itself. That leads to the final and deepest wall, entropy. The second law of thermodynamics states that disorder increases, energy disperses, and usable power diminishes. The stars themselves are engines burning through finite fuel. The universe once blazed with light, but in the far future, it will fade. Black holes will evaporate. Atoms will decay. Radiation will thin into silence. This is heat death, the end of all gradients. When no difference remains to drive work, no spark remains to power thought or travel. If this vision is true, then the ultimate limit of travel is not distance but duration. No matter how far we go, one day there will be nowhere left to go. But even before heat death, expansion sets another horizon. The fabric of space itself is stretching, carrying galaxies away from one another. The farther a galaxy is, the faster it recedes. Beyond about 16 billion light years, they move away faster than light relative to us. We cannot chase them, not because of our engines, but because the road itself grows faster than we can run. Every day, more galaxies cross that threshold, slipping beyond reach forever. The observable universe shrinks in practical terms. 100 billion galaxies today may dwindle to only a few visible in the future. Travel across the cosmos is not simply difficult, it is diminishing. With each moment we hesitate, more of the universe is lost to us. These walls paint a grim picture. Speed limited, energy scarce, time relentless, expansion merciless, entropy final. Against them, our ambitions look fragile, even absurd. Yet even within these walls, possibilities remain. The Milky Way alone offers hundreds of billions of stars, countless planets, endless potential. Travel to even a fraction of them would be more than enough to fill millions of histories. Cosmic limits are not the end of dreaming, they are the frame that gives our dreams shape. And perhaps these walls are not absolute. Physics is incomplete. What we call laws may one day be seen as approximations, local rules in a larger, stranger reality. Just as Newton's laws gave way to Einstein's, perhaps Einstein's will give way to something beyond. We cannot know. But the fact that we can ask is itself extraordinary. The universe has produced beings capable of questioning its limits, of imagining travel across gulfs that dwarf them. That capacity is a kind of travel in itself, a movement of thought, not matter, but no less profound. So how far can we really travel? The sober answer is this: not beyond light speed, not beyond entropy, not beyond expansion. These are the hard edges of the map. Yet within them lies more space, more possibility, more wonder than we could ever exhaust. Perhaps the point was never to escape the walls, but to explore the room they enclose. To live, to travel, to dream within the boundaries of physics is still to embrace infinity. For infinity is not only distance, it is also the unending depth of meaning we find in the journey itself. We began with a simple question: how far can we really travel in space? But the answer has unfolded into something much larger. Distance led us to energy, energy to survival, survival to meaning. Each horizon revealed another, not only in space, but in thought. The farther we try to go, the more the question turned inward, asking not just about ships and stars, but about what it means to be human at all. At the most literal level, the universe has given us boundaries. Light speed is a wall. Entropy is a law. Expansion is a thief, stealing galaxies from view as space itself stretches. Against these realities, our ambition seems fragile. The dream of reaching distant galaxies may be impossible forever. Even within the Milky Way, the gulfs are so immense that to cross them will require civilizations capable of endurance far beyond our current scale. We are small, brief, bound. The cosmos is vast, ancient, merciless. That is the sober truth. And yet, that is not the whole truth. For within these limits lies abundance beyond comprehension. Even if we never leave the Milky Way, hundreds of billions of stars remain. Even if we never surpass light speed, nearby systems beckon: Proxima, TRAPPIST-1, Tau Ceti. Hundreds of Earth-like worlds scatter like stepping stones across our spiral arms. Even if entropy one day claims the last spark of heat, the window before that spans trillions of years, more than enough for thousands of civilizations to rise, flourish, and fall. The walls of the universe are not cages, but horizons, enclosing not emptiness, but endless possibility. The question of travel, then, may never be answered by physics alone. It must be answered by us. Do we endure long enough to build generation ships, to adapt to alien seas, to send seeds of our species into the dark? Do we master energy without destroying ourselves? Do we learn humility enough to live alongside other biospheres, if we find them? Do we preserve meaning as we scatter, ensuring that even when distance erodes identity, the story of who we are continues? These are not questions for equations. They are questions for culture, philosophy, morality. How far we can travel will depend not only on the universe, but on our wisdom. The silence of the galaxy looms over us still. Perhaps others tried and failed. Perhaps others remain hidden or transcended, indifferent to the paths we now dream of walking. Or perhaps we're first, the fragile dawn of intelligence in the cosmos that has waited 13 billion years for us to open our eyes. If so, then the responsibility is staggering. How far we go will determine whether the universe remains silent or begins to sing. And yet, even if we never leave this solar system, even if human feet never press into alien soil, we have already traveled far. Voyager, a machine no larger than a truck, has left the sun's influence and now drifts in interstellar space. Our radio signals cross the void, faint whispers racing outward at light speed, carrying music, mathematics, and greetings in dozens of languages. Our telescopes peer across billions of light years, touching galaxies we will never reach. In thought, in imagination, in wonder, we have already crossed the universe. Travel is not only propulsion, it is perception. It is curiosity. It is daring to ask the question at all. Perhaps this is the deepest answer. How far we can travel is not measured only in kilometers or light years, but in meaning. To step onto the moon was to travel farther than any distance suggests, because it redefined what we believed possible. To send a probe beyond the sun's influence was to extend humanity's reach into the cosmos in a way no number can capture. Each step changes us, and in changing us, expands our horizon. Far is not fixed. It is whatever lies beyond what we thought was possible yesterday. The universe will not make it easy. It has set the rules, drawn the boundaries, written entropy into its bones. But within those rules, we remain free. Free to build, to dream, to voyage. Free to decide whether the story of our species ends on one small planet or unfolds across countless suns. Free to choose whether silence remains or is broken by voices carried to the stars. In the end, the true measure of distance is not how far we can go, but how far we dare to imagine. If we believe that Proxima Centauri is too far, then the journey ends here. If we believe that galaxies are too far, then they will remain forever out of reach. But if we accept the vastness and choose to try anyway, then every limit becomes a milestone, every wall a challenge, every horizon a promise. The cosmos may be merciless, but it is also generous. It has given us a mind that can ask, a spirit that can yearn, a will that can push against the infinite. So how far can we really travel in space? As far as the laws of physics allow? As far as our energy can carry us? As far as our civilizations can endure? As far as our meaning can stretch without breaking? Perhaps that is not to the ends of the universe, nor even to the next galaxy. Perhaps it is simply to the next star. But even that would be enough. To cross that first gulf is to declare that distance is not destiny. To reach another sun is to prove that intelligence can step beyond its cradle. To carry our story into the stars, however far, is to transform silence into song. The universe is watching. Time is waiting. The choice, as always, is ours. It is tempting to close the book here, to say we have asked the question and offered an answer. But the truth is that such a question has no ending. How far can we really travel in space? Is not solved once, but asked again in every generation, in every society, in every mind that looks up at the night sky and wonders. Each era redefines both its limits and its possibilities. What felt impossible centuries ago, flight, spaceflight, even standing on the moon, are now memories, part of our history. To stop asking will be to stop moving. To stop moving will be to stop being human. When we talk about traveling far, we imagine rockets and engines. But there are other kinds of travel already underway. We travel with our machines Voyager drifting into interstellar darkness, Perseverance roving the Martian dust, telescopes stretching our sight into galaxies billions of light years away. We travel with our data radio signals leaking outward like invisible lanterns, carrying our laughter, our music, our arguments, our entire civilization, encoded in electromagnetic whispers. We travel with our imagination stories of alien worlds, starships, and futures that may never come to pass but inspire us nonetheless. In many ways, we are already traveling farther than our bodies will ever go. But imagination has weight. Dreams shape actions. The rockets we build, the probes we launch, the technologies we invent, all begin as ideas. The Apollo program was not just an engineering project. It was a story a nation told itself about what was possible. Interstellar travel, too, will begin as a story. The idea that we could step beyond Earth is not fantasy but necessity, not myth but blueprint. The first generation that builds a ship bound for another star will do so not because physics suddenly changed, but because belief did. Yet belief without responsibility is dangerous. Traveling far means carrying our flaws as well as our brilliance. Every ship will contain not only hope, but conflict. Every colony will inherit not only survival skills, but divisions, prejudices, and struggles. The vastness of space will not erase what we are, it will magnify it. A quarrel on Earth may scar a village. A quarrel on a ship traveling for centuries could destroy an entire venture. If we carry violence and short-sightedness into the stars, distance will not save us. It will only doom us farther from home. To travel far requires not only engines but ethics, not only power but wisdom. Perhaps that is the real measure of distance, how far our values can stretch. Can cooperation endure when home is 4 light years away? Can compassion extend across centuries, when the children who arrive are strangers to those who left? Can humility guide us if we find we are not alone? The answers to these questions may decide more than any equation of speed or energy. They may decide whether humanity's story becomes a constellation of flourishing worlds or a scattering of ruins. And still, the stars invite us. Each one rises not as a warning, but as a promise. They burn indifferent to our struggles, but in that indifference lies opportunity. They will not wait forever cosmic expansion steals more every day, but they wait long enough. The question is not whether we are allowed to go, but whether we will choose to. Will we look at the night sky and see distance, or will we see invitation? Will we shrink before the scale, or will we dare to move? If history teaches us anything, it is that we move. Always. The first people who left Africa for unknown lands had no guarantees. The sailors who crossed oceans knew nothing of what lay beyond the horizon. Each risk carried fear, and each journey carried cost. But each step opened new worlds. Space is simply the next ocean, the next horizon, the next test of who we are. The risks are greater, the distances larger, the costs immense, but so too are the rewards. To travel far is to secure not only survival, but significance. For in the end, travel is not just about where we arrive. It is about what we become by daring to leave. To stand on another planet, to see another sunrise on another world, is to prove that intelligence can step beyond instinct, that life can expand beyond its birthplace, that the universe can be known not only through light but through presence. Even if we never reach the edge of the cosmos, to have reached even one more star is enough to change the story of existence forever. So, how far can we really travel? As far as we choose to carry our imagination, as far as we are willing to stretch our endurance, as far as our values can withstand the test of distance and time. The stars will not close their gates. The universe will not say no. The only true limit is whether we say no to ourselves. And if we say yes, if we dare, if we try, if we endure, then the question will not end here. It will echo again, asked by the children of those who leave Earth, asked on new worlds with alien skies, asked under constellations rearranged by perspective. How far can we travel? They will ask, as we ask now. And their answer, too, will not end, because travel is not only a destination. It is a condition of life. It is a story of intelligence itself. And as long as we exist, As long as stars burn, as long as time itself holds open a path, the question will live. The answer will change. The journey will continue.